All right, good morning, everybody. We're going to start. So go ahead and spend a couple minutes working on these warm-up problems. Basically, we're going to use the rules for derivatives, which we learned in the last lecture, to warm up with some of these guys, and then we'll go ahead and learn some more derivative rules. So go ahead and take a couple minutes here and try those problems out, and then we'll talk about them. All right, would anybody like a little more time to finish up? Is everyone finished? Okay. So what I want to start with is first by asking you guys which rules you think we're going to need to apply on each of these problems. And the reason that I'm asking that is because when you're doing derivatives, I think it's a really important or helpful skill to be able to take a look at the problem without doing any work and decide ahead of time which rules you think you're going to need, okay? And this will help you to just look at a problem, know that you have to do the derivative, and just by looking at the function, have an idea of where you're going before you start. Okay, so look for the signs that tell us to use certain rules. So, of the derivative rules that I mentioned last time, which I'll briefly remind you were, God, why does this always happen? The rules were multiplication by constant rule, power rule, sum and difference rule, derivative of a constant rule. Yeah. We also had a rule for doing the derivative of a linear function, but that's just a combination of the power rule and the constant rule. Okay, if I have mx plus b, actually it's a combination of the power rule, multiplication by constant rule, and derivative of a constant rule. The derivative of a constant rule tells us that this b is just going to go away. The power rule says that m times x to the negative, or m times x to the 1 will become 1 times m times x to the 0. So this will be 1 times m times x to the 0. Okay, so that linear rule is really just a combination of these rules. Okay, so these are the 4 rules that we've learned so far. Which rules am I going to need to use to do problem A? Or maybe I can just have people give me one rule at a time. Yeah, Ryan?
The power rule.
We're going to need to use the power rule for sure. The clue is, well, I have a power of x. That's the clue that's telling me I need to use that rule. All right, next rule, yeah?
The derivative of a constant.
Yeah, we're going to need to use the derivative of a constant rule. Derivative of constant. And how do you know you're going to need to use that rule?
Just a constant.
Yeah, one of the summands in f of x is a constant. All right, and the last rule, there's one more rule that we're going to need to use.
The sum difference rule.
Yeah, the sum and difference rule. By the way, is this too small up here for you guys to read? Okay. All right, yeah, so the last one is sum and difference rule. Specifically, we're going to use the sum component of that rule. All right, so all together, who can tell me what this derivative is going to be? Yeah, Mary?
Just 2x.
Yeah, just 2x. Very good. All right. Next, let's move on to C, actually. Let's talk about the rules that we're going to need to use to do C. What are we thinking there? Yeah, Kevin?
The power rule.
Power rule. How do you know that we're going to need to use the power rule?
Because the square root of x is going to become x to the 1/2.
Yes, doing a square root is the same as doing the power of 1/2. So I'm going to need to use the power rule. Any other rules? Nope, just that one, right? So first we got to rewrite this thing as x to the power 1/2. Then the power comes down. So h prime of x will be equal to 1/2 x. What should the new power be? Mia?
Negative 1.
Negative 1/2, exactly. I just subtract 1 from the old power. And if I wanted to write it all together nicely, I'd write 1 over 2 root x, something like that, maybe. All right, great. The next two I'm going to go through rather quickly. Looking at this, I can see I'm going to need to use power rule twice, actually. I'm going to need to use the sum and difference rule. Or, well, really, I guess the difference rule. All right, and I think that, oh, and one more rule, multiplication by constant. All right, so the derivative of 2x cubed, I just take that 3 down front, I let the 2 kind of float, and I wind up with 2 times 3x squared minus, when I'm doing the derivative of this 7x thing here, I can kind of think of it in one of two ways. I can try to use my derivative of a linear function as just the slope, so 7x would become 7. Or I can think about the 7 floating and then use the power rule on x. Okay, the power rule on x would say x to the power 1 becomes 1 times x to the power 0. In other words, 1. Okay, so I would get 6x squared minus 7. Questions on part B? All right, this multiplication by a constant rule is really convenient. We can just, instead of having to do the derivative of all of 2x cubed, I just let the 2 hang out and I do the derivative of x cubed and then multiply. All right, great. Last one here. I think I'm going to need to use the power rule. And I'm going to need to use the sum rule. I think there's one other rule that I'm going to need to use. Can somebody help me out? What's the other rule? I've got power rule and sum rule.
Constant, multiplication by a constant.
Yeah, multiplication by a constant rule. Okay? X over 2. Let me write this down here. X over 2 is the same as 1/2 times x. Hopefully you all agree with me about that. So division by a constant can be reframed as multiplication by the reciprocal. So since I'm doing division here, it should be that. I'm also going to need to use the multiplication by a constant rule on the 2 over x squared, because I can rewrite 2 over x squared as 2 times x to the negative 2. So that 2 there is just going to float like usual. Okay, so multiplication by constant. So if we do it, this would become, first of all, I'm going to rewrite it in a rule-friendly way. I'm going to let those constants float. And now I'm going to write the derivative of x to the negative 2. Well, that's just going to be negative 2x to the negative 3. And I'm going to add 1/2 times the derivative of x. Well, that's just 1. So I get negative 4 over x cubed plus 1/2. And I really shouldn't have written an equal sign here, because guess what? These two things are not equal. The thing on the bottom is the derivative of what's on the top. So what I should have written instead is f prime of x. Make a new statement. Okay. Great. Any questions about the warm-up problems or rules that we covered last time? No questions at all? Great. Okay. So now we're going to talk about some new rules. And I'll tell you in advance, I'm a little bit peeved that the book gives you this second rule here at this point. But I've been following the book so far, so I guess I'll keep doing it for now. In fact, these first two really are a repackaging of a rule that we're going to learn later on called the chain rule. It's extremely important. So later on when I talk about the chain rule, I will when I talk about the chain rule, I will kind of talk about these two examples and why they are an example of the chain rule. For now, I'm just going to give you the rules, okay? So if we want to do the derivative of, remember that's what this notation means, do the derivative of a to the power x, where a is some number. It could be 2 or pi or negative a billion, some kind of number, but not 0. Okay, not 0. Oh yeah, I guess it should be positive as well. So let's make sure that we have a greater than 0. If we want to do this derivative of a to the power x, it's going to be a to the power x times the natural log of a. for now, I'm asking you to take me at my word on that. The book doesn't give any real justification for why that's true until we get to the chain rule. So that's when I'm going to talk about why this rule is true. But for now, we're going to memorize it and use it to compute some stuff. All right. So that's that. So, for example, if I wanted to do the derivative of 2 to the x, its derivative would be 2 to the x times ln 2. Okay? Remember this ln of a here is just a number. So it's just some constant that's being multiplied by a to the power x. All right. The next one we're going to learn is the derivative of e to the power kx. This one's a little bit easier to learn. And it's the classic example of the chain rule. If we want to do the derivative of e to the k times x, we just get e to the k times x times k. All right, now this is just a special case of the last rule. We said that we can do this derivative of a to the power x for any positive number a. Well, if we just used, for example, the number e, right, then we would get e to the x times ln of a. Or ln of e, excuse me, which ln of e would just be 1. All right, so that's what's going on here. Well, actually, let me take a step back. I'll add an extra page and really explain what I was talking about there. Let's be specific. So how can I use the rule d dx of a to the x equals a to the x times ln a? If I set a equals e to the k, then we are doing d dx of e to the k to the power x, which is the same as doing d dx of e to the power kx. Okay, and then this left-hand side thing, using our rule, should be equal to e to the k to the x times ln of e to the k. And this is equal to e to the kx times ln, well, ln of e to the k is just k. So that's why it's a special case of the first rule. All right, so if you're clever, you can get away with just memorizing 1. We can use the same trick to try to talk about a to the power x. We can repackage it in terms of the other way. We can just say, well, a is equal to e to the ln of a, and then we can just use, say, a to the x is just equal to e to the ln of a to the power x is just equal to e to the ln of a times x. So if we want to do the derivative of the a to the x, we can write it like this and just use the e rule. So you only really need to memorize 1 as long as you have a good grasp of how to play with e and ln, which, based on the exams, some of you need some refreshers on doing that. So, questions about these two rules so far? If you want, you can put these on a flashcard, put them under your pillow at night, and hope you absorb them into your brain. I think it's going to make a lot more sense once we talk about the chain rule. All right, so now we're going to do the derivative of ln of x. This is a pretty easy one. If we just do d dx of ln of x, we just get 1 over x. All right, so the derivative of ln of x is just 1 over x. All right, let me think for a second here, make sure okay. So we talked about all the rules so far that we're going to talk about today. So what we're going to do now is a bunch of combinations of the rules that we've already learned so far with the new rules that we just learned. And we're going to start combining more and more rules as we go on. We still have many rules left to go. We're going to learn the product rule, quotient rule, chain rule. Well, I guess that's it. But yeah, so we have some more rules coming. But now we've kind of expanded our arsenal, and it's time to try some new guns out. All right, so let's start with this first one, A. We've got 2 times 3 to the power x plus 5e to the x. Who can help me determine which rules I'm going to need to use to do this derivative, including old rules and new rules? Yeah, Ashlyn?
Would you use derivative of a positive number?
We're- Yeah, we're going to do the derivative of a to the x for a positive number a. That rule is going to be used on this part right here, this 3 to the x. So we will use deriv of a to the x. That's one of our rules. Any other rules? Yeah, Ryan?
Derivative of a constant times a function.
Yeah, multiplication by constant. That's one of our old rules. In fact, we're going to use it on both pieces. We're going to use multiplication by constant because we have a constant being multiplied out front of both of these things. Great. Any other rules? I can count 2 more rules. Yeah?
The sum rule.
Yeah, sum rule. Self-explanatory. Last one. What's the one thing that's not highlighted so far?
Derivative of e to the k.
Yeah, what's k?
1.
Yeah, 1. This is derivative of e to the kx, where in our case k is equal to 1. So that is this part right here on the end. Great. So now I know all the rules that I'm going to use, so I'm just going to do them. First of all, I know these constants are just going to float. So I'm going to write 2, and then next to 2, I'm going to write the derivative of 3 to the power x. I just learned that rule. The rule says that the derivative of 3 to the power x will be equal to 3 to the power x times ln of 3. So 3 to the x times ln of 3. Plus, the 5 is going to float. Now I need to do ddx of e to the kx, where k is equal to 1. Well, looking at the right-hand side of that rule, highlighted in green up here, I know I'm going to get just e to the kx again times k. If k is 1, that just turns out to be e to the 1 times x times 1, which is just going to be e to the x. Oops. E to the x. Great. So, all in all, we would write, I don't know, 2 ln 3 times 3 to the x plus 5e to the x, I guess, if you want to rearrange it a little bit. Okay. I think it's really useful to be kind of breaking down these rules like this, because a lot of students tend to just kind of like hack away piece by piece, and they often tend to forget something in the end if they don't start with an idea of where they're going. Especially when we get more complicated rules going forward. All right, who can help me with part B? We'll do part B as a team. Mary?
Derivative of a to the x.
Yeah, we're going to need to use deriv of a to the x. Anything else?
Derivative of e to the kx.
Great. Anything else?
And a constant.
Derivative of a constant. And one more rule, I think. Yeah, Ashley? Yeah, sum rule. So who can tell me what my answer is going to be? Kevin?
Is it e to the x plus 2dx times ln 2?
Perfect. What happened to the constant? Just went away, right? Because derivative of a constant is 0. All right, I'm going to speed up a little bit and do a couple more examples from this section. So we've got 8x squared plus 8e to the x plus 8 times 4 to the x. So in my mind, I see automatically we're going to need to use multiplication by constant rule. We're going to need to use power rule. That's all just in the first term. The second term, we're going to need to use multiplication by constant and derivative of e to the kx. The last term, we're going to need to use multiplication by constant and derivative of a to the x. And all of these things are being added together, so I'm also going to need to use the sum rule. That's how I look at one of these problems when I initially start, because I've had a lot of practice with the rules. You'll get there sooner or later. So let's just go ahead and start. The first one, I know that 8's going to float. This is going to become 16x squared, because I multiplied down that 2, not x squared, sorry. It should be just 16x. Because the power of x became 1 less, we multiplied down the 2. All right, we already saw how to do the derivative of just e to the x. It's the easiest derivative there is. You don't do anything at all. And now I need to do 8 times the derivative of 4 to the x. I'm using the rule here where I do the derivative of a to the x. It says the derivative should be a to the x times ln of a. In our case, 4. So that would be my answer. Did I go too fast for anybody there? Should I go back and dig into any of that? Yeah?
What's like the sign between the 8 and the 4? Is that just like, is that what?
Multiplication. Yep, multiplication. It's kind of inherited from right here.
Oh, from up there, okay.
Yeah, it's good notation to write it like that. So thanks for reminding me. Any other questions? All right. I'll do part E here. Looking at it, I can immediately see I'm going to need to use the multiplication by constant rule. I'm also going to need to use the power rule on 17x. I'm also going to need to use the rule for e to the kx on e to the 1/3 x. And I'm going to need to use the rule for a difference of two functions. Jumping right in, I know these constants are going to float. The derivative of e to the 1/3 x is just e to the 1/3 x again times 1/3. Now I subtract 17 floats, x becomes a 1. So my answer is 5e to the 1/3 x minus 17. Yeah.
Is there any particular like order you want us to write them in, or like how simplified we need to make it?
I will say if you write this on your exam, I would give you full credit. I might not be super happy about it, but I'll give you full credit. What I wouldn't give you full credit for is if you wrote something like 15 times d dx e to the 1/3 x minus 17. I wouldn't be happy with that, because although you showed that you can see that the constant can be pulled out, you didn't show that you know what the derivative of e to the kx is. So if you wrote something like that, you wouldn't get full points on your problem. You'd probably get, well, however many proportional points you would get for doing 2 out of 3 rules or something like that. Yeah, if your answer is equivalent to the real answer and you don't simplify, that's okay in my book. All right, unless the directions say something like simplify completely, then you should simplify. Any questions about these problems on number 1, just applying our new rules in combination with our old rules? Maybe I should ask, which of the new rules is the most confusing? Any thoughts? I guess we haven't really done one with ln, have we? So I guess which of those 2 rules is more confusing, a to the x or e to the kx? Do you have a preference? Or is it all just so easy that you don't even feel comfortable saying one's hard? Yeah, Andrew? Yeah, I agree. I don't like doing the derivatives of a to the power x because, well, e to the power x is so easy. You just rewrite the exact same thing that you had before, and then you write whatever the number is that's in the power, k. Whereas I tend to forget whether it should be ln a after or something else. So I much more often in my mathematical career, I use this e to the kx rule, and when I have to do the derivative of a to the x, I just rewrite it like how I wrote it on this second page, and I just use that rule because I don't have space in my brain for more rules. All right, we'll move on and do some other stuff. So now we got some ln problems. Great. Ooh, I like this one. Okay, we'll start. First things first, we'll do A. So, the rules I'm going to need to use: multiplication by constant, sum rule. What other rules do I need to use? Yeah, Ryan? ln rule. 2 more rules. Yeah, Andrew? Power rule. Very good. Last rule. Yeah, Ashlyn?
Just a constant.
Just a constant rule? Oh, sorry, I should have said 2 more rules. Kevin, you know the last one? Yeah, e to the kx rule. Okay, just because it's a t now, you still got to use it. Great. So, 5 floats. What's the derivative of ln of t? Yeah? 1 over t. Perfect. plus 7, derivative of e to the t. Well, that's the easiest one there is. Just e to the t. Minus 4t squared. What does that become? Yeah, 8t. So since we're subtracting it, we keep that negative sign right there. And then the minus 12 becomes minus 0. So I'm just not going to write it. So altogether, we get 5 over t plus 7e to the t minus 8t. Okay. Let's talk about C. C is a fun one, I think, because there's a pitfall kind of lying in wait. Which rules are we going to need to use to do the derivative of 4e cubed plus 2.45 ln of t? Ashlyn?
Derivative of EKX.
Anything else?
Would it be the LN?
ln rule. 2 more rules. One of them is the sum rule, and the other one's the multiplication by constant. One of the rules that's written down here, I actually don't have to use. Does anybody know which one it is? Kevin?
E to the kx.
Yeah, why don't I need to use this top rule here? Yeah?
Because 4e to the 3 is just going to be one number.
Exactly. So the critical thing here is there's no t in our exponent. This is just e to the k. It's not e to the kx. So since there's no variable in our power, e cubed, you can literally type it in on your calculator. You'll get some wonky number. Then multiply it by 4, you'll get some other wonky number. But it is just a number. So we actually won't need to use this rule. What we'll use instead is a derivative of a constant. Okay? So since I don't have this t here, the derivative of this whole first thing is just going to go away. It's going to be 0. And we'll have f prime of t is equal to 2.45 over t. All right. That's another one of those tricky things, like, you know how we keep doing those problems where I put in pi and I'm like, is anything different now? And invariably somebody says, no, pi is just a number. Same deal with this e stuff. If we just have e to some power, it's still just a number. But if we have e to a power times t, or e to the power times some variable, then we got to be a little careful and use our rule. Okay, thank you, Ashlyn and Kevin, for that. I think we've seen enough examples. Let's do a word problem. Oh, great, another tangent line problem. All right, we're supposed to find the equation of the tangent line to g of x equals 2e to the x plus 3 at x equals 0. So, first of all, let's recall what is the formula for the tangent line. T of x equals, who can tell me what I should write down? Yeah, Mary?
F of A plus F prime of A times X minus 1.
Very good. Something that I talked about with some students that I was working with yesterday, I had to substitute for a class, and they were a little bit confused about where this formula came from. So one student asked me, where does this come from? It looks like you just wrote down a bunch of random jazz. And you're like, that's the equation, and they didn't really feel like they had a good connection for why this represents the equation of the tangent line. And so what I did was I said, well, if we just moved t of x over, or if we moved f of a over to the other side, and I put it in parentheses like this, and I said that that's equal to f prime of a times x minus a, then I said that this kind of looks like, y minus y naught equals m times x minus x naught. Do you see the similarities between these equations? And they actually mean the exact same thing, because in our equation, f of a and f prime of a and a are just numbers. And those are exactly the numbers y naught, m, and x naught. So remember, when we talked about point slope form, we said that this is the equation of a line with slope m which passes through the point x naught comma y naught. So our equation is equation of a line with slope f prime of a which passes through the point a comma f of a. So if we were to draw our graph, and this was a, then this point right here would be the point a comma f of a. And if we made the slope of the function equal to the derivative at that point, then our line would be the line which passes through that point and has slope equal to the derivative of the function, which is exactly what the tangent line is. Okay, so to answer that student's question, this was the response I gave. It's really just coming from point slope form, rearranged a little bit. All right, I'm going to erase everything except for this top line here. Is that okay? So I can actually do the problem. Great. Man, I made a lot of little tiny marks. Come on. All right. So, the key pieces of information that I need to know that I don't know right now are what is f of a, what is f prime of a, and what is a. The first one I can see straight from the problem. A is going to be 0. Okay, great. So now I need to know what is f of 0. Well, I get f of 0 by just plugging in the 0 into 2e to the 0 plus 3. E to the 0 is 1. So if I multiply it by 2, I get 2. And I add 3, I get 5. To find f prime of 0, I first need to find f prime of x so that I can plug it in. So f of x is equal to 2e to the x plus 3. So I'm going to apply the constant rule, multiplication by a constant, and I'm going to apply derivative of constant, and I'm going to apply derivative of e to the kx, where k is equal to 1. So when I do that, and I compute this derivative, what should I get? Ashlyn?
2e to the x.
Yep, just 2e to the x. And if I plug in 0, I'll get 2e to the 0 equals 2. All right, so now I know f prime of 0, I know f of 0, and I know what a is. So all I have left to do is just plug into my original formula. T of x is equal to f of a, I'm just going to write 5. F prime of a, I'm going to write 2. And I'm just going to write x here, I guess, because x minus 0 is just x. So I could use this line to approximate the function near x equals 0. So maybe if I wanted to know what is the value of g of 0.1 or g of negative 1/9, some value which is close to our 0, then I could just plug it into this formula, t of x, which is quite easy to plug numbers into that thing. I don't even need a calculator. However, it won't be exactly equal to the value of g, which I would need a calculator to find out, but it will be kind of close. All right. Questions about the tangent line problem? Okay. I think these tangent line problems are some of the trickier ones to do. Just because I think that a lot of students get confused by this formula up here at the top, this t of x formula. And at first glance, it looks very unfriendly because we see all these f's in here. We've got an f of a and an f prime of a, and we're kind of confused about what a is and what even are these things, but we got to remember that they're not functions. If we plug a number into a function, we get back a number. So this f of a here is just a number. This f prime of a is just a number, and a is just a number. And so this whole thing just looks like the equation of a line, which you've seen many times probably since you started doing algebra. All right. Suppose $2,000 is deposited into a savings account earning 8% compounded continuously. Oh God, we haven't seen a compounded continuously problem for a while. Find an equation for the balance f of t after t years. And then we're supposed to find and interpret f of 20 and f prime of 20. Okay, so what's the general formula for f of t gonna be if we have continuous interest? Just looking for a general formula here. We don't have to plug anything in from the word problem. It should be of the form something, something, something. Somebody help me? Nobody feels confident about that. All right, I'll write down two equations, and you tell me which one is right. Sam?
P naught e to the kt is compounded continuously.
Yeah, the compounded continuously formula is this second one here. P naught e to the kt. P naught is going to be our initial deposit, 2,000. K is going to be our continuous interest rate, 0.08. So f of t is equal to 2,000 e to the 0.08 t. While we're at it, why don't we compute f prime of t? I'm just going to use the rules that I learned today. This 2,000 is going to float, and I'm going to multiply times e to the same thing as before, and then I have to remember that I multiply by k, which in our case, k is 0.08. So, they ask us to find and interpret f of 20. Well, f of 20 is equal to 2,000 e to the 0.08 times 20. And if I plug that into my calculator, I would get some number. And this is amount of money. in bank account after 20 years. If I plugged in f prime of 20, I would get 0.08 times 2,000 times e to the 0.08 times 20. And that would be some number, and that would be the rate at which money is growing in dollars per year at the end of the 20th year. Not enough space. Yeah, Ryan.
Can you go through the rules on how you got f prime of 20?
Yeah, sure. First of all, we're done with class. Sorry, I went 1 minute over. If you want to leave, you can leave. And don't forget, you have a homework assignment due tonight and every Friday. There's a new one up for next week. If you find issues with it, please email me and let me know, and I'll help you troubleshoot that. All right, Ryan. So you wanted to go through the rules on how I did this derivative, right?
Yeah.
Okay, great. So we're just going to consider what's happening in this green square and not worry about any other part of the problem. I wanted to do the derivative of 2,000 times e to the 0.08t. The rules which I used here were multiplication by constant and derivative of e to the kx. So remember, we had d dx of e to the kx equals e to the kx times k. So, in our case, our application of this was d dx of e to the 0.08t equals, and we just use this exact formula here. So e to the kx stays exactly how it was. And then we multiply by k, where k is the number that's attached to the variable, which is 0.08.
So then for the f prime of 20, you just put the 0.08 in front instead of...
Exactly. So the only difference between f of 20 and f prime of 20 is that we multiply 0.08.
Okay.
Yeah, that's exactly the right idea.
Okay,
Mm-hmm.
thank you.
Yeah, no problem. Any other questions for you two? You good? Sweet. Have a good weekend.